Alright, so just a quick video going over this this error that I made. So I posted the correction up. This is slide 31 of chapter 5. So I've got the correction right here. The thing that I overlooked was there was friction, right? So there's friction between M1 and the surface. So we handled friction in this problem, so we're going to do the same thing. Very, very similar to what I did. I just didn't account for friction. So you see the setup is the same. Okay, so the initial energies of M1 and M2 are both the same as they were before. Right, system starts from rest. Nobody has a kinetic energy. M1 doesn't have a change in gravitational potential because it stays up on the table, same vertical position. M2 goes from a gravitational potential of M2GH to 0 because I'm in amber. So the only thing that's different here is that we have to account for the work due to friction. Okay, so the work by a non-conservative force in this case is not 0. All right, so if this was 0, delta E, or E final minus E initial, would equal 0. So E final would equal E initial. But since there is work due to friction, the work is due to the change in energy. Friction is going to take energy out of the system. It's a dissipative force. The system is going to lose energy, and we'll see that just like in the example following this, the work is negative. Right? This work is going to be negative, so delta E is going to be negative, which means the energy is decreasing. I have to use a dot product definition of work, which is the force times the force vector dot product with the displacement vector. The distance that M1 slides across the surface is the same height that M2 falls. So D is equal to H, just like in the slide 32 example. D is equal to H. Friction is equal to mu times the normal. What's the normal force? If I draw a free body diagram for M1, normal, right? The normal force is equal to M1G. So the normal force is equal to M1G. The frictional force is equal to mu M1G. So mu M1G is my frictional force. H is the distance, or the displacement vector of M1. The angle between the friction force and the displacement vector is 180. That's where we get our negative sign from. Cosine of 180 is negative mu M1GH. That's the work due to friction. So now, instead of the sum, or the change in the energy, being equal to 0, the sum of the energy is equal to the work due to friction. So the process is the same. The only thing you'll notice is that you've got an extra term over here. Right? Before I was solving for V, and I didn't have anything over here. Right? So this term was equal to just M2GH. Right? Final kinetic was equal to M2's initial potential. Now the final kinetic is equal to the initial gravitational potential minus the work being done. Okay? So work is being taken out. The total energy of the system is going to decrease. So algebra is still the same. Again, I just have this extra term right here, this negative mu M1GH. So my algebra is still the same. I know everything that I need to know. The only thing is this term makes everything under the radical smaller, right? Because I'm subtracting this from this term. And so we'll end up with a speed that's actually less than my original answer, which makes sense, right? The energy from the system is lost. So the whole system is going to have less kinetic energy, which means the two objects are going to have a speed that's smaller than when I neglected friction. Okay, so the process is the same. This is actually a good, happy accident, as my wife would say. We've got the energies, right? Initial and final. We set it up the same way. So these are not. This is actually good two examples, right? One where there's friction, and then one, my mistake, where there's not friction. Okay, where there's not friction, energy was conserved. I went through the same process, right? I have this formula right here. I just set the work equal to 0. The final energy was equal to the initial energy, and I got a speed. Now that I account for work, is taking the friction's taking energy out of the system, so I get a lower speed. So this will be good practice. You can practice this problem with and without friction, just to prepare yourself for two different types of energy problems we'll see Friday. One last thing, the last slide on chapter 5 is on power. I didn't give any examples, and there might be an occasional portion of a WebAssign problem that asks you for the power. Power is just defined as the change in a system's energy with respect to time, right? So it's the rate at which energy is being transferred into or out of a system. How do we transfer energy into or out of a system? We do work on that system, okay? We do work on that system. So it's work divided by time, or it's the change in total energy divided by time, all right? So friction is actually taking power out of a system, right? Because the work is negative, so we'd have negative power, all right? The unit is the joule per second, which we call the watt, okay? Named after James Watt. So it's a joule per second, it's a watt, okay? And basically what's going to happen is we're going to go through a conservation of energy problem, or we'll go through a problem where there's work being done. Right? We'll go through a problem where there's work being done, and then we'll do something like either the time will be given in a WebAssign problem. I think usually they'll give you the time, so it's just work over time, and you just calculate the power, which is, again, pretty straightforward. Anytime you're doing a power problem, find the net work done on the system, or the change in the system's energy, divided by the time it takes for that energy transfer to take place, and then you've got the power. Sometimes they might not explicitly give you the time. Look for an opportunity to use either kinematics or Newton's second law, right? If you have the acceleration and you know it's like, you know the system's starting from rest, right? You could use a kinematics equation or a pair of kinematics equations to find that time, okay? So if you're not given the time, just go back, look at all the quantities you have, and then use kinematics, possibly Newton's second law. On occasion, you might have the velocity of a system later and the force acting on it, right? Like if it's the frictional force, you could do this too. But 9 times out of 10, we've got to calculate the work anyway. So just look for an opportunity to use kinematics and the information you're given to solve for time. Divide that work by the time, and you've got the power. Okay. Any questions on Chapter 5? Let me know. Again, I can communicate through email. We can set up a Zoom thing, whatever you want to do. So, good luck. Exam 2 is Friday. It's going to be the same structure, same format. 8 in the morning to 8 at night. You've got 3 hours to complete it. It's on chapters 4 and 5, everything we cover this week. Okay? Good luck. Email me. You need to Zoom or something like that for my office hours or outside of office hours, whatever you need to do. Anytime before like Thursday night. Okay? Thanks.